Hello everyone, Greg here, and this morning we are going to discuss eddc608 week 3. Our primary topic this week is called correlation. So first of all, what do we mean by correlation? Well, let's take an example. Let's say on this axis we have the number of carrots you eat per day. You could either eat 1, 2, 3, or 4 carrots per day. And on this axis is the number of miles you run in your workout. So if you were to put these data pair on a graph, we would find here that we ate 1 carrot per day. We could run 1 mile. If we ate 2 carrots per day, we ran 3 miles. If we ate 3 carrots per day on another day, we ran 2 miles. And if we ate 4 carrots per day on another day, we ran 2 miles. So the goal of correlation is to see how well bivariate data pairs fit a straight line. Now, when you use the Wasserstats calculator, which is provided in your content, that's a very good one to compute the R, which is the correlation coefficient. And make sure that you're computing the R, not R squared, okay? So as you know, R's that are very close to 1, or R's that are very close to -1, are perfect correlations, meaning the data pairs would lie on a line. Now, one of the things that gets confusing is the R measures the degree to which the points fit a straight line. It doesn't tell us anything about the slope of the straight line. So we could have an R of 1 with an infinite number of different lines. Okay? The actual slope of the line is called the regression equation. And that's not what we're dealing with right now. We are dealing merely with correlation. So I went to the Wasserstats calculator and I put these pairs in. When you start the calculator, it asks you for an N. That's the size, that's the number of pairs in the sample, of which case there's 4. So I put in 1, 1, 2, 3, 3, 2, 4, 2. And when I clicked calculate, I came up with an R of 0.316. Now, that R of 0.316 is considered a weak correlation, meaning these points don't fit very close to a straight line. Well, the other thing that you need to know is you need to look at the two-tailed p-value, which it will show you just below the calculations. In this case, the two-tailed p-value is 0.6838. Well, what does that mean? That is important. All right, one thing to note is that this set of data is merely a sample. It's merely a sample. And like all inferential statistics, we need to draw a conclusion about the population. So the population of all the carrots that could possibly be eaten and the population of all the miles that could be run. This is merely a sample. Now, one of the things that gets confusing in correlation, if you look at page 239 in your text, the null hypothesis in correlation always is that there is no correlation in the population. So let's say you believed that there was a relationship between the number of hours you slept and your IQ. I don't know how that would work, but the null hypothesis would be that there's absolutely no relationship between the number of hours that you sleep and your IQ. So it's upon the researcher to show that there potentially is a relationship. As a result, the alternative hypothesis is that the correlation in the population is not 0. Therefore, some correlation exists. So this is very important. Now, in our first example, our two-tailed p-value of 0.68 is greater than 0.05. Now, 0.05 is our standard alpha in research, and since the p-value, 0.68, is larger than 0.05, we say that the result is not significant. It is not significant, meaning we cannot reject the null hypothesis that there is no relationship between carrots and miles you run in the general in the general population. There's not enough evidence to support that. Okay? So, it's important to pay attention to the p-value, and this will come up more as we do more work in hypothesis testing. Now, let's say that we change the data, and I'm going to go back to the calculator, and I'm going to change the pairs to 1, 1, 2, 2, 3, 3, and 4, 3.5. So, if I were to put those pairs on the graph, it would look like this. 1, 1, 2, 2, 3, 3, and 4, 3.5. Not quite a straight line, but pretty close. As a result, when I run the correlation coefficient calculator, I get an R of 0.99. Now that R of 0.99 means that those points are almost on a straight line. Of course, an R of being 1 means that the points are in a straight line. Well, the other thing to note is that the p-value is 0.01. Now, what does that mean? Remember, if the p-value is 0.01 and it is lower than 0.05, that means the result is significant. Now, what does it mean for this result to be significant? If we take our null hypothesis that the number of carrots you eat is not related to the miles you run at all, since the p-value is less than our alpha of 0.05, we can reject this null hypothesis in favor of the alternative, which is that there is some relationship between the number of carrots you eat and the number of miles you run in the general population. Now, that's not the general population of people, that's just the general population of all carrots and the general population of all miles. So that's very important. In correlation, the null hypothesis plays a very important role. The null hypothesis always is that there is no correlation in the general population. So you have to have, with a sample, you have to have a very strong correlation to show significance to reject that null hypothesis in favor of the alternative, which is that in the general population of data pairs, there would be a correlation. Okay, so we'll discuss more of this week. Essentially, that's how it works. And if you have any questions, let us know. Have a good day.